EG1301 Separation Methods in Chemistry, Unit 4 Specific Chromatographic Techniques. In this unit, we are going to discuss the point third Introduction to Ion Exchange Chromatography. I am Dr. Devang Pandya from the Department of Chemistry, St. Xavier's College, Autonomous, Ahmedabad. We are going to discuss these syllabus points today. Principle of ion exchange chromatography, classification of ion exchange reagents, properties of ion exchange reagents, factors affecting ion exchange separations, application of ion exchange reagents. Ion exchange chromatography. Before that, we need to discuss or learn what is chromatography. The process or technique of separating molecule molecules or components in a mixture solution, gas or liquid, according to the differential absorption and elution is known as chromatography. Chromatography first invented in 1906 by a Russian botanist Mikhail Tsvet. You can read the autobiography of Mikhail Tsvet on net and learn more how he has identified the ion exchange chromatography and on which molecule has used this technique. Chromatography is the physical separation of a mixture into its individual components, used in qualitative and quantitative analysis of biological and chemical substances. So that is the application of ion exchange chromatography, that it can be used in the qualitative and quantitative analysis of biological and chemical substances. The principle of ion exchange chromatography. Different affinity of different components to stationary phase causes the separation. On this principle, ion exchange chromatography works. It means when we use word ion, then ions have different charge. They have positive, negative, opposite charge, similar charge, opposite charge attract each other, similar charge repels each other. So different ions have different affinity, and that concept has been utilized in ion exchange chromatography, that different affinity of different components to stationary phase causes the separation, and that is how the separation take place in ion exchange chromatography. This technique employs two immiscible substances, mobile phase and stationary phase. These two phases must be immiscible. They are made of substances which must be immiscible with each other. Between these two, this technique can be used. Mobile phase. The solution of gas or liquid components works as transporter, moves in a definite direction. These transporters, which is in a moving in different direction, they are considered as mobile phase. And the mobile phase is made of either gas or either liquid component, and they act as transporter and moves in a specific direction, and they have different affinity. On the stationary phase, they cause that due to this different affinity on different components, this mobile phase is going to separate the component of the chemical constituent, and that is how the ion exchange chromatography works. Now, which kind of stationary phase is required in ion exchange chromatography? liquid or solid absorbs or impacts different components of the solution to different degrees. This kind of absorbent or solid or liquid compound act as stationary phase, but these two different phases, mobile phase and stationary phase, should be such kind of compound which should be immiscible substance with each other, and they have different affinity with a different component of the compound of the stationary phase, and that cause the separation. So this is the principle of ion exchange chromatography, in which two type of phase is utilized, that is mobile phase and stationary phase, and they have different characteristic as well. Now, types of chromatography. uh, First is absorption chromatography. Second is a partition chromatography. Third is our ion exchange chromatography. Fourth is molecular exclusion chromatography. Fifth one is affinity chromatography. Out of these five, we need to discuss ion exchange chromatography in depth. So here our ion exchange chromatography is there. Ion exchange chromatography separation is based on the charge. This, you may say, the specific quality of ion exchange chromatography, or you may say this is the limitation of ion exchange chromatographic separation. That if the compound which we want to separate from each other, if they do not possess charge, then ion exchange chromatography is not used for such compound. It means that the compound must have different charges on it. Then and then only ion exchange chromatography separation technique can be employed to separate those components from each other which contain charge. So this is the special case, we can say, for ion exchange chromatography, or we, on other sense, we can say that this is the limitation of ion exchange chromatography. This technique used for almost any kind of charged molecules. Large protein molecules would be there, small nucleotides, amino acids, such kind of biochemical compounds which we can separate through this technique. Condition is that they must have charged molecules. Ion exchange chromatography preserves analyte molecules on the column base on ionic interactions. Stationary phase would be such kind of reagent which is used to covalently attach ions or anions or cations onto it. And mobile phase is useful for opposite charge solute ions to be attracted to the stationary phase by electrostatic force of attraction. That way, these two phases have different tendency. One is going to have a covalent attachment with anion and cations onto it, and the other have uh, electrostatic force of attraction with the charged solute ions, and that way the separation in ion exchange chromatography taken place. Now, the principle of ion exchange chromatography. Ion exchange chromatography relies on charge-charge interactions between the proteins. Mixture of similar charged ions separated by using ion exchange reagent. Reversible exchange of similar charged ions, cations or anions can be separated through ion exchange chromatography. So the principle, reversible exchange of ion present in the solution and ion exchange reagent. The mechanism of separation will be the exchange of ions from column to the solution. Now, classification of reagents. According to the chemical nature, they can be classified as strong cation exchange reagent, weak cation exchange region, strong anion exchange region, and weak anion exchange region. So this four category would be there. On the nature of the chemical, we can classify the regions. Now here you can see that the type of resin, strongly acidic cation exchanger, in which we have sulfonic acid group attached to styrene and divinyl benzene copolymer, and the usual form as purchased, that is aryl SO3H, that is the cation, and as far as the market brand name is concerned, Amberlite IR 120 and Dovex 50W act as this kind of resin, and it can selectively separate silver, rubidium, cesium, potassium, ammonium, sodium, hydronium, lithium, zinc, copper, nickel, and cobalt kind of ions. Selectively, it can separate out this kind of cations. Weakly acidic cation exchanger, carboxylic acid group attached to acryl and divinyl benzene copolymer, usual form as purchased, that is RCOONA plus, and brand name as Amberlite IRC50, and selectively it can separate out H plus, Ag plus, K plus, Na plus, Li plus, H plus greater than Fe plus 2 greater than Ba plus 2, Sr plus 2, Ca plus 2, and Mg plus 2. So this is the order selectively it can perform cation exchanger. Sodium plus, which is a strongly basic anion exchanger, in which quaternary ammonium group attached to styrene and divinyl benzene copolymer, where the main group as the exchanger, that is aryl CH2N CH3 thrice Cl, and it is known as commercially Amberlite IRA 400 or Dovex 1, and these are the ions, and the order of ions for selectivity of this resin is there. This is only strongly basic anion exchanger, N plus greater than, that is typological mistake. Now weakly basic anion exchanger, that is polyalkyl amine groups attached to styrene and divinyl benzene copolymer. The main group act as the exchanger is aryl NHR2 Cl minus, that is Amberlite IR45 or Dovex 3, and this in this order selectively it can separate the compounds. Now classification according to the source. Natural source, as far as cation is concerned, zeolites or clay can be used, or as far as anion is concerned, dolomite, and synthetic anion is concerned, inorganic or organic resins can be used. Organic resins, they are the polymeric resin matrix. The resin composed of polystyrene, sites for exchangeable functional groups would be there, and divinyl benzene, that is cross-linking agent, offers a stability to this different kind of resin exchanger. Ion exchange chromatography employs the dynamic interaction between the charged solute ions and stationary phase that have oppositely charged groups. In separation of these simple ion and ions of like charge in the mobile phase compete for sites on the stationary phase. Similarly, you can see that A minus, and here X plus B minus. Now it's going to exchange B minus, and A is going to replace B minus, so it is anion exchanger. Similarly, cation is there and it's going to exchange B, so it is a cation exchanger. The magnitude of the ions competition with B for the charged site X will govern their retention. Generally speaking, this type of chromatography may be used to separate ionic species such as organic acids or bases, which can be ionized under specific pH condition. In addition to the reaction with ionic sites on the stationary phase, retention may be affected by the partitioning of solutes between the mobile and stationary phases, as in reversed phase chromatography. Consequently, even no ionized solutes may be retained on ion exchange columns. As discussed previously, ion exchange chromatography is an adaptable technique used primarily for the separation of ionic or easily ionizable species, which already I have said earlier. The stationary phase is characterized by the presence of charged centers having exchangeable counter ions. So there must be exchangeable counter ions that must be charged species. Then and then only ion exchange chromatography can be proceeded. This you may say the speciality of ion exchange chromatography, or you may say limitation of ion exchange chromatography as well. Both anions and cations can be separated by choosing the suitable ion exchange medium. Ion exchange is applied in essentially all branches of chemistry. In clinical laboratories, it is used on a routine basis to profile biological fluids and in the diagnosis of various metabolic disorders. You may consider this an application of ion exchange chromatography as well. Ion exchange has been used for many years as the separation mechanism is in automated amino acid and carbohydrate analyzers. Ion exchange chromatography was introduced more recently to separate a broad range of biological macromolecule, big size molecule using special wide pores, low capacity packagings that were designed for this purpose. Ion exchange may be used to separate neutral molecules as their charged bisulfite or borate complexes, and also certain cations as their negatively charged complexes. For example, we have FeCl4-. In the case of borate complexes, carbohydrate compounds that have vicinal diol group can form stable charged adducts that may be resolved by anion exchange chromatography. Ligand exchange chromatography has been used with cation exchanger in the nickel or copper form for the separation of amino acids and other bases. Ion exchange packings can be used to separate neutral and charged species by mechanisms that do not involve ion exchange. For example, oligosaccharides and other related material can be separated by a partition mechanism on ion exchange columns where water or either alcohol mobile phases are employed. On the basis of their degree of non-exclusion from the resin pores volume, ion exclusion may be used to separate charged species from uncharged species and also charged species from one another. An ion exchange packaging that has the same charge as the sample ions is used for this purpose. Retention depends on the degree of sample access to the packing pores volume. The separation of organic acid with a cation exchange packing in the hydrogen form is an example of this mechanism. Strong acids are totally excluded and elute early. Weak acids are somewhat excluded and have intermediate retention values, and the neutral molecules are not affected by the Denon membrane potential and can explode the total pore volume. The packing for ion exchange chromatography are typified by the presence of charge-bearing functional groups. Sample retention can be envisioned as a simple exchange between the sample ions and those counter ions that were originally attached to the charge-bearing functional groups. However, this simple illustration is not a good portrayal of the actual retention process. Retention in ion exchange chromatography depends on factors other than Coulombic interaction. Hydrophobic interactions between the sample and non-ionic regions of the support are important with organic ions. As far as example, since the mobile phase is often of high ionic strength in ion exchange chromatography, hydrophobic interaction were favored because of the salting out effect. Salting out effect from a qualitative point of view, the retention of organic ions most likely proceeds by a hydrophobic reverse phase interaction with the support, followed by diffusion of the sample ion to the fixed charge center where an ionic interaction takes place. Diffusion controlled process influence both column efficiency and sample retention. Following steps can be considered for that: ion diffusion through the liquid film surrounding the resin bead, diffusion of ions within the resin particle to the exchange sites, actual exchange of one counter ion from another, diffusion of the exchanged ions to the surface of the resin bead, and diffusion of the exchanged ion into the bulk solution through the liquid film surrounding the resin bead. Slow diffusion of the sample ions within the resin beads has a significant detrimental effect on the column performance. Reducing the particle size to less than 10 mm in diameter makes up for the poor mass transfer kinetics exhibited with conventional resin beads by reducing the length of intraparticulate particulate channels. Because the column packings used in ion exchange contains charged functional groups, an equal distribution of mobile phase ions both inside and outside the resin bead involves in accordance with the Donan membrane's effects. The ion exchange bead act like a concentrated electrolyte solution in which the resin charges are fixed while the counter ions are unrestricted. The contact surface between the resin bead and the mobile phase can be seen as a semi-permeable membrane. When equilibration occurs between the external and internal solution and one side of the membrane contains a non-diffusible ion, then a combination of the Donan membrane effect and the need to preserve overall electric neutrality results in a higher concentration of free electrolytes within the bead. Thus, diffusion of sample ions and counter ions across the Donan membrane barrier is generally the rate controlling process in ion exchange chromatography. Selective series have been established for many counter ions, like as far as cation is concerned, lithium is less than hydronium, less than sodium, less than ammonium, less than potassium. This is the series for the cations. And as far as anion is concerned, fluoride less than hydroxide, less than acetate group, and so on. So these are the order of the selectivity of cations or anions in the as a counter ions. The absolute order relates to the individual ion exchanger, but deviation from the above order are usually insignificant for the different cations and anion exchanger. HPTLC is preferred over any common cation for weak acid resins, while hydroxide ion is preferred over any of the common anion weak base resins. So this hydronium is preferred for cation or for weak acid resins, while hydroxide ion preferred over any common anion weak base resins. When a choice of the column type has been made, sample resolution is optimized by adjusting the ionic strength, pH, temperature, flow rate, and concentration of buffer or organic modifier in the mobile phase. A summary of the effect of these parameters on solute retention is given in the table in this next slide. There you can see that in the table, factors influencing the retention in the ion exchange chromatography is given. Here is the mobile phase parameter, where ionic strength is there, pH is there, temperature is there, flow rate, buffer salt, organic modifier, and another organic modifier is there. These are the mobile phase parameter which can alter the retention in the ion exchange chromatography and influence on mobile phase property, that is solvent strength through ionic strength, solvent strength through pH change, solvent selectivity through pH change, efficiency through temperature change, efficiency through flow rate disturbances, solvent strength and selectivity through buffer salt change, solvent strength differences through organic modifier, and efficiency through organic modifier as well. Now, what effect through these changes in the mobile phase affect on the retention? So if we have a mobile phase parameter like ionic strength which can change the solvent strength, the solvent strength generally increased with an increase in ionic strength. Selectivity is little affected by ionic strength except for sample containing solutes with different valence charges. The nature of mobile phase counterion controls the strength of the interaction with the stationary phase, and that way the strength of solvent is affected by ionic strength. Similarly, these different parameters have different effect on the sample retention in ion exchange chromatography. The temperature at which the separation are performed is another variable that can have a marked effect on the separation. Temperatures up to 50 degrees centigrade or 60 degrees centigrade often result in employed separation because of reduced viscosity and improved mass transfer. The solute stability at this higher temperature should be resolved prior to use. So that is enough from my side and for the ion exchange chromatography. If you have any kind of doubt, any question, query, don't be negative, be positive and ask me either in the Moodle chat box or either you may email me your queries. So thank you very much. Let's see some video based on the ion exchange technique instruments.
Buffer systems are used to create pH or salt gradients for pH scouting. In combination with the Agilent 1260 Infinity BioInert LC system, Agilent Buffer Advisor software helps you to automate the blending of these buffer systems, eliminating the tedious and error-prone steps associated with manual buffer mixing. A typical application of ion exchange chromatography is the analysis of proteins. Buffer systems ensure that the proteins remain in their native states. Proteins consist of amino acids. Their amine and carboxylic acid functional groups make them amphiolites or Switter ions. Depending on the pH of the surrounding media, the protein's net surface charge can change. Under high pH conditions, the protein's surface charge becomes more negative. In contrast, low pH conditions make the protein's surface charge more positive. The pH value at which the protein's net surface charge is equal to 0 is called the isoelectric point, or PI. Let us now take a look at a hypothetical protein with an isoelectric point, or PI, of 7. In a buffer solution of pH below 7, the protein's surface charge is more positive. And in a buffer with pH higher than 7, the surface charge is more negative. This phenomenon is utilized by ion exchange chromatography to separate charged species. In a low pH buffer where the protein's surface charge is positive, a cation exchanger with a negatively charged solid support is used for separation. In this example of cation exchange chromatography, a buffer keeps the pH constant while a salt or ionic strength gradient, commonly with sodium chloride, is used to create the separation conditions. The proteins bind to the solid support in the column according to their relative surface charges. By increasing the salt concentration or ionic strength of the mobile phase, the less strongly bound proteins are desorbed by the positively charged sodium ions and elute first from the column. As the ionic strength increases, the more strongly bound proteins are desorbed and eluted. In the following example of pH scouting, salt gradients at different pH values are used to optimize the separation of 3 proteins. In this example, using the Agilent 1260 Infinity BioInert LC, salt gradients are created at pH values from 5.8 to 6.8 in steps of 0.2. Giving a total of 6 different chromatographic methods. Even small differences in pH lead to significant changes in separation performance. The salt gradient at pH 6.8 yields the best separation. In contrast to a salt or ionic strength gradient, a pH gradient uses a mixture of buffers consisting of a binding buffer with a low pH, such as pH 3, and an elution buffer with a high pH, such as pH 9. This technique is called chromatofocusing. In this example of cation exchange with an anionic solid support, the starting pH of the binding buffer is low. This leads to a more positive surface charge on the proteins. The proportion of the elution buffer is then increased, leading to a higher pH and generating a pH gradient within the column. The proteins migrate to the pH region that corresponds to their respective PI value. As the pH is increased further by addition of more elution buffer, the protein's surface charge becomes more negative. As a result, they are desorbed and eluted from the column. Agilent Buffer Advisor software provides a fast and simple way to create multiple salt and pH gradients.
Separation in ion exchange chromatography depends upon the reversible adsorption of charged solute molecules to immobilized groups of opposite charge. Most ion exchange experiments are performed in 4 main stages: equilibration, sample application and wash, elution, and regeneration. The first step is the equilibration of the stationary phase to the desired start conditions. When equilibrium is reached, all stationary phase charged groups are associated with exchangeable counterions, such as chloride or sodium. The second step is sample application and wash. The goal in this step is to bind the target molecules and wash out all unbound material. The sample buffer should have the same pH and ionic strength as the starting buffer in order to bind all appropriately charged proteins. In the third step, elution, biomolecules are released from the ion exchanger by a change in the buffer composition. A common way is to increase the ionic strength with sodium chloride or another simple salt in order to desorb the bound proteins. Proteins are desorbed relative to the number of charged groups on their surface. The final step, regeneration, removes all molecules still bound. This ensures that the full capacity of the stationary phase is available for the next run.
आयन एक्सचेंज रेजिन्स वो पॉलीमर्स हैं या क्रॉस लिंक पॉलीमर्स हैं जिनके पास कुछ केटायंस या एनायंस होते हैं जो फ्री केटायन या एनायन की तरह बिहेव करते हैं। और कैसे फ्री केटायन या एनायन की तरह बिहेव करते हैं कि उसके चारों तरफ का जो एनवायरनमेंट या मीडियम होता है उसमें अगर कोई आयन प्रेजेंट है उसके साथ वो एक्सचेंज कर सकते हैं अपने आयंस को जो उनके पॉलीमर मैट्रिक्स में अवेलेबल है। तो इन तरह के पॉलीमर्स जिसमें ये कैपेबिलिटी पाई जाती है कि वो अपने आयंस को एक्सचेंज कर सकते हैं जिस एनवायरनमेंट में या जिस सॉल्वेंट में उसे रखा गया है उसके साथ, तो वो पॉलीमर्स कहलाते हैं आयन एक्सचेंज रेजिन्स। आयन एक्सचेंज रेजिन डिपेंड करता है कि उसमें किन तरह के आयंस का एक्सचेंज वो रेजिन कर सकता है। तो इसमें हम 3 तरह के केसेस ले सकते हैं, जिसमें सबसे पहला केस है कि कैटायन एक्सचेंज रेजिन। कैटायन एक्सचेंज रेजिन वो होंगे जो जिनके पास कैटायंस अवेलेबल हैं और वो कैटायंस एक्सचेंज हो सकते हैं एनवायरनमेंट के साथ। दूसरा क्लास है एनायन एक्सचेंज रेजिन्स। इनके पास एनायंस अवेलेबल हैं और ये एनायंस एक्सचेंज हो सकते हैं एनवायरनमेंट के साथ। और तीसरा क्लास है जिनके पास कैटायन और एनायन दोनों अवेलेबल रहते हैं, इन्हें हम कहते हैं एम्फोटेरिक एक्सचेंजर्स। एम्फोटेरिक एक्सचेंज रेजिन्स। एम्फोटेरिक एक्सचेंज रेजिन्स वो होंगे जिनके पास कैटायंस और एनायंस दोनों अवेलेबल हैं और वो कैटायंस और एनायन दोनों को एक्सचेंज कर सकते हैं एनवायरनमेंट के साथ। कैटायन एक्सचेंज रेजिन का स्ट्रक्चर यहाँ दिया हुआ है। ये जो कैटायन एक्सचेंज रेजिन्स में यहाँ हम देख सकते हैं कि ये एक पॉलीमर मैट्रिक्स है जिसमें ये बेंजीन रिंग्स में कुछ ग्रुप्स यहाँ दिखाए गए हैं। ये इन ग्रुप्स में आप देख सकते हैं कि H+ आयन है। ये H+ आयन एक्सचेंज हो सकते हैं एनवायरनमेंट में जो भी प्रेजेंट कैटायंस होंगे उनके साथ। तो ये होगा क्या इस केस में कि ये H+ आयन सॉल्यूशन में चले जाएंगे और वहां पर जो अवेलेबल होगा कैटायन वो यहाँ आके इनकी जगह ले लेगा। तो ये कैटायन एक्सचेंज रेजिन्स यूज किए जाते हैं नॉर्मली वाटर सॉफ्टनिंग के केस में, कि वाटर में जो कैटायंस और एनायंस अवेलेबल हैं जो मौजूद हैं जो हार्डनेस प्रोड्यूस करते हैं वाटर में, उसमें से जो कैटायंस है वो यहाँ इस कैटायन एक्सचेंज रेजिन के थ्रू एक्सचेंज किया जा सकते हैं। तो उसमें से कैटायंस रिमूव किया जा सकते हैं। और यहाँ दिख रहा है कि अगर कैटायन रिमूव होगा तो वाटर में क्या जाएगा H+ आयन ये हार्डनेस प्रोड्यूस नहीं करेगा। तो ये जो कैटायन एक्सचेंज रेजिन्स हैं ये पॉलीमर मैट्रिक्स एक नॉर्मल जैसे हम देख सकते हैं कि ये स्टायरीन डाइविनाइल बेंजीन का ये पॉलीमर मैट्रिक्स है जिसमें कुछ ग्रुप्स हैं SO3H+ जिसमें से H+ आयन एक्सचेंज हो सकता है। तो ये रेजिन कहलाता है कैटायन एक्सचेंज रेजिन। यहाँ आप देख सकते हैं फिगर है एनायन एक्सचेंज रेजिन्स का। एनायन एक्सचेंज रेजिन्स के भी केस में जैसे कैटायन एक्सचेंज रेजिन में आपने देखा कि ये स्टायरीन डाइविनाइल बेंजीन पॉलीमर मैट्रिक्स क्रॉस लिंक पॉलीमर मैट्रिक्स जो है उसमें वहां SO3H ग्रुप था जिसमें से H+ आयन एक्सचेंज हो सकते थे एनवायरनमेंट के कैटायंस के साथ। यहाँ पर आप देख सकते हैं कि ये जो ग्रुप है CH2NMe2 OH, ये ग्रुप्स, इन ग्रुप्स में OH माइनस हाइड्रोक्सिल आयंस अवेलेबल हैं। ये एनायंस हैं जो कि एक्सचेंज हो सकते हैं जिस एनवायरनमेंट में इस रेजिन को रखा जाएगा। तो ये जो एनायन एक्सचेंज रेजिन है ये भी यूज किए जाते हैं कहाँ, वाटर सॉफ्टनिंग के केस में, क्योंकि वाटर में हार्डनेस प्रोड्यूसिंग केटायंस और एनायंस दोनों होते हैं। तो केटायन एक्सचेंज रेजिन के थ्रू हम केटायंस को रिमूव कर सकते हैं और एनायन एक्सचेंज रेजिन के थ्रू हम एनायंस को रिमूव कर सकते हैं। यहाँ ये जो OH माइनस आयन है ये एक्सचेंज किया जाएगा किससे, वाटर में जो भी एनायंस अवेलेबल हैं जो हार्डनेस दे रहे हैं। तो ये OH माइनस यहाँ से रिमूव कर दिया जाएगा और यहाँ पर जो एनवायरनमेंट में जो या जिस सॉल्यूशन में इसे सॉल्वेंट में लिया गया है उसमें जो एनायंस अवेलेबल हैं वो यहाँ आके अटैच हो जाएंगे। तो एनवायरनमेंट से एनायंस रिमूव किया जा सकते हैं। तो ये दोनों रेजिन्स वाटर सॉफ्टनिंग के केस में यूज
Ion
किए जाते हैं।
exchange chromatography is a method used to separate or concentrate biomolecules based on their charge. The stationary phase of an ion exchange column is a matrix which consists of insoluble charged polymers that contain loosely held ions that are exchangeable with the target molecule. The charge of the target molecule, which is pH dependent, determines the type of matrix used. At pH 7, cytochrome C has an overall positive charge. Therefore, cation exchange chromatography is used to target this protein. In today's lab, the cation exchange chromatography procedure will involve resin equilibration, sample application to the resin collection, and finally, elution of cytochrome C. Resin equilibration. Cation exchange resin beads are equilibrated using 2 washes of 0.1 molar sodium phosphate buffer at pH 7. Sample application to the resin. The negatively charged resin will bind cytochrome C while the sodium counter ions are displaced. In this way, cytochrome C is concentrated on the resin. Resin collection. The resin is collected into a syringe column and non-bound substances drain out of the column. Elution of cytochrome C. To elute cytochrome C from the column, a buffer solution with a higher concentration of sodium ions, 0.8 molar sodium chloride, is used. The increased ionic strength of the solution will result in sodium replacing cytochrome C on the column.